Here we are given 6 graphs of functions and asked to determine which of the graphs possibly represent polynomial functions. Some characteristics of the graphs of polynomial functions. One is they are smooth. What we mean by that is there are no sharp corners. Another characteristic of polynomial functions is that they are continuous. There's no breaks in the curve. You could draw the whole thing without picking up your pen or pencil. And a third characteristic is that the graph will go to either positive or negative infinity far to the left or to the right. So the curve tends to infinity or negative infinity. Far to the left or right. So let's use those 3 characteristics to determine which of these graphs could represent polynomial functions. There's no guarantee that it is a polynomial function. It's just likely. So if we look at this first curve that's labeled f of x, there are no sharp corners. It appears to be smooth, and it's continuous. I can draw the whole curve without picking up my pen. The curve, does it tend to infinity or negative infinity far to the left or to the right? Well, far to the left, I see the curve tending to negative infinity, and far to the right, the curve is tending to negative infinity as well. This is possibly a polynomial. All right, let's look at the graph that's been labeled g of x. Let's see what we have here. We have a smooth curve. There's no sharp corners in this curve. But wait, I just had to pick up my pen. Right? If I draw the curve from left to right, the curve goes here, and then I have to pick up my pen and jump here. That's a break in the curve. What we might learn about later on in a course is that this curve has what's called a vertical asymptote in the curve. And that's a break. That's what we call an infinite discontinuity. This cannot be a polynomial. It has a discontinuity in the curve. All right, let's look at the third graph, which has been labeled h of x. And from left to right, it's smooth. And then at this point, there's a break. I have to pick up my pen and jump to the next point. There's a break in this curve, right? That's what we call a jump discontinuity. This is not a polynomial. All right, let's look at k of x. Curve looks smooth. There's no sharp corners. Continuous. I can draw the entire curve without picking up my pen. All right. Does the curve tend to infinity or negative infinity far to the left or to the right? Far to the left, it tends to negative infinity. Far to the right, it tends to positive infinity. This is possibly a polynomial. All right, let's look at the curve called m of x. Smooth. Yeah, this is a smooth curve. Continuous. It is continuous from left to right. I can trace the entire curve without picking up my pen. Part 3, does the curve tend to infinity or negative infinity? So here, if I move far to the left, this part of the curve is not moving downward. It's not going to negative infinity. That's not tending to negative infinity. Similarly, far to the right, that part of the curve is not tending to positive infinity. It's flat, it's horizontal. And actually, these are what we call horizontal asymptotes to the curve. This is not a polynomial function. In a later course, you might study functions that look like this. It's called a logistic curve or a logistic function. All right, and finally we have n of x. Let's look at this. So this curve, n of x, is not smooth. We have this sharp corner here. Actually, we would call it a cusp for the curve. It is not smooth at that point. And so it fails that first condition. This is not a polynomial. All right, so I hope that gives you an idea of how to identify polynomial curves.